discuss the master theorem discuss discuss the asymptotic notation. In this class, we want to discuss about properties of asymptotic notations. Okay, properties of asymptotic notations. Now we know which are the different asymptotic notation. What is the meaning of asymptotic notation? And we also discussed some examples. Okay, so which are the different asymptotic notations? Big O notation, then theta notation, then big omega notation. Other notations are little O notation, little O, big O and little O, and little omega or small omega. These are the different notations we are commonly using. Okay, so what are the properties of asymptotic notation? First property is you can expect a 4-mark questions from this section. Okay, just a descriptive topic. So in the just in the point of view of exam. Okay, so which are the different properties of asymptotic notation? One property is transitivity. The transitivity property is satisfied. So what is transitivity? What is transitivity? You know what is transitivity? For example, f of n is equal to theta of g of n, and g of n is theta of h of n. Then f of n is equal to theta of h of n. So that is transitivity property, and the same can be applied for other notations also. There are some other notations like big O, little O, omega, little omega, etc. We can apply the same concept. Okay, that is transitivity can be applied for all relations. All notations. Okay. Okay. Next is reflexivity. So what is reflexivity? F of n into theta of f of n. Okay. This is true for big O and big O. Okay. Please note the notation. This is big O notation. This is big omega notation. This is theta notation. So f of n is equal to theta of f of n. F of n is equal to big O of f of n. F of n is equal to big omega of f of n. So this is reflexivity property. Then symmetry. Then we want to discuss the symmetry property. Okay. Okay. Then we want to discuss the symmetry property. So what is symmetry property? F of n is equal to theta of g of n. Then g of n is equal to theta of f of n. Okay. This is symmetry property, and this is true for the theta relation only. Okay. This is the theta relation, and the symmetry property true for the theta relation. This is the theta relation. Okay. Theta relation. Okay. You know what is symmetry property? A is equal to b, if and only if b is equal to a, like that. So f of n is equal to theta of g of n, if and only if g of n is equal to theta of f of n. This is true for theta notation. Okay. Theta notation. Okay. Okay. Theta notation. Okay. Anaka. Hello, Anaka. Okay, connection പോകുന്നുണ്ട് ഇൻഫോം ചെയ്യണം. ഞാൻ ചെക്ക് ചെയ്യാൻ വേണ്ടിയിട്ടാണ്. Okay. 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 Next, transpose symmetry. Another property is transpose symmetry. Transpose symmetry. And this is the concept. F of n is equal to big O of g of n, if and only if g of n is equal note these notations. Okay, big, this is big O, this is big omega. Okay, g of n is equal to of f of n. F of n is equal to little omega. Sorry, little o. This is little o notation. Little of g of n if and only if g of n is equal to little omega of f of n. This is transport symmetry property. Okay, so we discussed 4 properties, and from the exam point of view, they may ask questions what are the properties of asymptotic notation. You can expect 3 or 4 marks from the section, so you can answer these questions. You can write this. Okay. So there are 4 properties. One is transitivity, another is reflexivity, third is symmetry, and fourth is transport symmetry. Some other properties also there, but we just want to focus on this. Okay. Next, we are moving to the different complexity functions. Okay. So now we studied different time complexity functions. Okay, which are the different time complexity functions? So common complexity functions we are using. Okay, in this topic, we are just understanding different time complexity functions we are using, and the order of growth is very important concept. Common complexity functions and order of growth. Okay, so which are the different functions using, and what is the order of growth of that functions? Okay, so usually we know we are measuring the time complexity in terms of the complexity functions, in terms of functions. Okay, like n, log n, etc. So what is the order of growth? Okay, this means what is the order of growth of this function we want to familiarize. Okay, there is next okay. Okay, chat box attendance ഒന്ന് ഇടുക എപ്പോഴും ഓർഡറിൽ ഇടാൻ ശ്രദ്ധിക്കും. ഓക്കെ, അറ്റൻഡൻസ് പിന്നെ എടുക്കും, ഒന്ന് ഇപ്പോഴും ഓർഡറിൽ. ഓക്കെ, നെക്സ്റ്റ് these are the different functions we are using. Okay, one is constant time function. Okay, some algorithm will take a constant time. Okay, for example, 3 or 4 steps which not at all depend on the input. Okay, so that type of functions is called constant time functions, and usually we will express it is in big of 1. Okay, big of 1. For example, suppose you developed an algorithm, and algorithm takes 4 steps, which is, and it is not at all depending the input, then it will take a constant time. So the constant time taking algorithm are represented in big of 1. Okay, also we can express theta of 1 or some other notation also, no problem, but here we are just expressing big of 1. Okay. Okay. Next is logarithmic time algorithm. Okay, and the root time algorithm is there. So we will express in log and the root time. So another complexity function is logarithm time functions and logarithmic functions. Okay, logarithmic function, it will take your, if your algorithm take logarithmic time, then it will be logarithmic time algorithm. Similarly, there will be some algorithm that takes root times. Okay, root n, where n is the input size. Okay, what is n? N is the input size. N is the input size. Okay. Okay. Where n is the input size. Then some other algorithm take n. Okay. Directly n. It is linear time. Okay. So there will be some algorithm that takes linear time. That is called big O n. So n is the function. T of n is equal to n. Okay. Next is linear logarithmic. It will take n log n time. Okay. Linear logarithmic time complexity functions is there. Then polynomial time complexity function. For example, big of n cube, n. You know what is a polynomial? Okay. Everyone knows what is a polynomial. So some time complexity functions is polynomial functions. Okay. For example, here I am writing n cube, n square. This n square is also called quadratic function. Okay. Quadratic time taking function. Okay. So n square is also the quadratic function. You know what is a quadratic equation? Degree of the quadratic equation is 2. Okay, so n square plus n plus 1 is a quadratic function. That type of functions can be implemented in this way, not candid in this way, big of n square. Another function is exponential function. Okay, so what is an exponential function? Note this, a raised to n, where a is a constant, but the power is n. N is the input size and power is n. So big of 2 raised to n, 4 raised to n, etc. Okay, this is called exponential function. So exponential function will take a lot of time. Okay, a lot of time to solve the problem. Okay, similarly, so another function is factorial time taking function, big of n factorial. These two are the extreme case of algorithms. Okay, these two algorithms will take a lot of time, even days or years, to solve the problem, depending on the input size n. Okay, depending on the input size n, these algorithms, exponential time complexity algorithms and factorial time algorithms, takes a lot of times, even days or years, to solve a problem. Okay, just try to understand. So next we are going. So in this, we familiarized which are the different complexity function. Okay, the simplest complexity function is big of n. Then next is log n and root n. Then next is n. Then next is n log n. Then next is n square, n cube, etc. And the last, then next is exponential, then factorial. Okay, this is the order of growth. That is, it will take time in this way. Okay. Okay, note this. While going down, the time complexity always increases. Okay, just note that point. Okay, while going down, the time complexity increases. Okay, so now just note this point, and these are the different complexity functions. Okay, next we are going to discuss plot of various time complexity function based on the order of growth. Okay. Now in the previous, here we familiarized which are the complexity functions we are commonly using. Okay, next we are trying to familiarize what is the order of growth of that complexity function. Okay. Okay. What is the order of growth of that polynomial function? So it is better to express in this way. Okay, this is the order of growth of the polynomial function. Okay, so there are some. This is log n. Okay, note this. This is the log n plot. You can view the plot. This is log n plot. Okay, this is log n plot. This is the log n plot. Okay. The lowest time taking algorithm. Okay. One more thing. In the x-axis, you will represent what the time. Sorry, the problem size. Okay. In this graph, in the x-axis, this is a graph, so we should know what is x-axis and what is y-axis. In the x-axis, we will represent the problem size n, and in the y-axis, we will represent the function. Okay, we are taking f. So if you are suppose you developed an algorithm and it is log n, it takes log n time, then the order of growth that function on the input size n is like this. Okay, this is the log n. Next, if it is n, the order of growth is in this way. That is, depending on the input n, the order of growth increases in this way. Okay, so next is n log n. Okay, note this order. First is log n, then n, then similarly there is root n not showing here, but log n and root n are almost same. Okay, next is n log n. Okay, so what is n log n? Linear logarithmic. Okay, linear logarithmic functions, n log n. And this is the curve of n log n function. So as the input size increases, time also increases linear logarithmically. Okay, this is the n log n plot. So it is somewhat complex, but you know, most of the sorting algorithms takes n log n time. Okay. Okay. Some sorting algorithms, bubble sort, etc. It's not bubble sort. Some other sorting algorithms will take n log n time. Okay. So another is n square, n cube, etc. This is the complexity. And this is the order of growth. This is the order of growth. Okay. It is look like this. And as the problem size increases, the time increases in this way. Okay, n square. And the last one is, here is 2 raised to n. This is the order of growth. As the problem size increases, the time taken increases exponentially. Okay, exponential time taking algorithm. This is one of the hardest or extreme cases of algorithms. Okay, just try to understand. Exponential time taking algorithm, and above that there is an n factorial algorithms. Okay, this is the n factorial. There are some algorithm that will take factorial time, and that is very complex case. Okay, n factorial, and below that 2 raised to n will come. Below that n square will come. Below that n log n will come. Below that n will come. Below that log n. Below that constant time. In this way. So this is the order of growth of various algorithms. Okay. So in the x-axis, this is the problem size, and f is the function. Okay, this express the time complexity function. As what will happen to the complexity function when n increases, that we want to find out. We can use this plot. Okay, so this is the order of growth of various algorithms. Okay. Hello, Sangeet. Sangeet. Okay, Vaishnavi. Anaka. Anaka, okay, കേൾക്കുന്നില്ലേ? Okay. Okay, mic open. Okay. Next, we want to discuss. So this is the plot here. We discussed that. Next, we want to move to this. We want just to familiarize order of growth table, and just for your understanding only, I'm saying this. And for example, you can note this table. Okay, so this also saying what will happen to the various function depending on the input size. Okay, what will happen to this is the input size, and what will happen to the various functions depending on the input size. Okay, so you can check this. When input size is 1, then logarithmic function takes 0 time, n log n is 0, n square is 1, n cube 1, 1, 2 raised to n is 2. So what is n is equal to 32? When n is equal to 32, then log n algorithm takes 5 steps only. Okay, 5 times it is executed. When n is to 32, n log n algorithms take 160 steps, 160 times to execute. Okay, 160 steps to execute. When n is equal to 32, n square algorithm will take 1024 times, 1024 steps to execute. When n is equal to 32, and n cube algorithm will take 32,768 steps. Okay, that is similarly when n is equal to 32, 2 raised to an algorithm take these amount of steps. Okay, you can note this. It's about 42 lakh or above. Okay, so that's why saying. So what you have to understand is that depending on the input size n, different functions will take different steps. Okay, and the extreme case here is for 2 raised to n. Okay, 2 raised to n is exponential time taken. Okay, so when the input size is 32, it takes these much steps to solve the problem. Okay. Just try to understand this table. Okay, just you don't want to study it by heart or anything, just for your understanding only I said this. Okay, depending on the input size n, then functions will take different number of steps or different time. Okay, just understand this concept. Okay. Next, discuss this also. Next, we want to discuss next I will give a problem. Okay, suppose an algorithm takes n raised to 10 steps. Okay. Suppose an algorithm takes n raised to 10 steps. Okay. Suppose an algorithm takes n raised to 10 steps. Okay. Which means what is the time complexity? It is big of n raised to 10. Okay. It is a polynomial time taking algorithm basically. N raised to 10 is a polynomial time taking algorithm. Okay. N raised to 10. Okay. So there is a polynomial time taking algorithm and so suppose you developed an algorithm that takes n raised to 10 steps. And the machine can execute. You are trying to run it on a machine. Okay. And suppose machine can execute 1 billion steps. Okay. 1 billion steps per second. Okay. So you can write in this way. 1 billion steps per second means 1 billion is 10 raised to 9. Okay. So what is 1 billion? 1 billion is 10 raised to 9. 1 billion is 10 raised to 9. Okay, 1 billion is 10 raised to 9. So the machine can execute 10 raised to 9 steps per second. Okay. So the question is how much time the machine will take when n is equal to 100. Sorry, n equal to 10. Okay, so the question, how much time the machine will take when n is equal to 100? So here n is actually the problem size. N is the problem size. And when n equal to 10, if you are giving, suppose you developed a sorting algorithm in your own ways. Okay, and time complexity is n raised to 10. Okay, then suppose you are giving a problem of input size n is equal to 10, then how much time the machine will take to execute? That you want to find out. Okay, so when n equal to 10, so we can solve this in this way. When n equal to 10, when n equal to 10, then number of steps needs to execute is 10 raised to 10. Okay, this is n raised to 10 actually. Number of steps, complexity of your algorithm is n raised to 10. But if n equal to 10, it will be 10 raised to 10. We can write in this way, 10 raised to 9 into 10. Is it possible? It's possible. Okay, we are writing in this way. So we know 10 for executing 10 raised to 9, how much seconds it will take? For executing 10 raised to 9 steps, how much seconds needed? You can know 1 billion steps, 10 raised to 9 steps per second. So, which means for executing 10 raised to 9 steps, only 1 second is needed. So, what will be the total time? Which is 10 seconds. Okay, try to understand the logic, and then you find out your algorithm. Your algorithm will take 10 seconds in your machine. Okay, so just try to understand the logic. In this way, we can find the execution time of various algorithms depending on the input size. Okay, this is a sample example. So you can note this is 10 seconds. 10 seconds is actually in terms of computer, 10 seconds is a very big time. Okay. You given an input, then you will wait for 10 seconds to get an output. It is very large actually. Okay. So is it an efficient algorithm? No, it's not an efficient algorithm. If there are some alternatives that takes below this time, then that will be the better one. Okay. Just try to understand that concept. Next, similarly, try to solve this problem. I didn't solve it, but using the above logic, okay, using the above logic, same logic, try to solve this problem. Okay, so suppose your algorithm take n cube steps. How much time will the machine will take when n is equal to 1000, n is equal to 10,000, n is equal to 1 lakh? You can expect this type of questions in the university exam also. Okay. Okay. Next. Okay. Next, we are moving to this chart. Okay. What is the effect of? You can note this and you can note this table. You don't want to study this, okay? I mean, just for your understanding only, I'm saying this, and don't want to worry about this, okay? So, suppose the same cases we are considering, and the machine can execute 10 raised to 9 steps, 10 steps in 1 second. Then, here, this is the problem size column. Here, this is the problem size. This is the problem size. Okay, n is equal to 10, n is equal to 20, n equal to 30, 40, and the problem size increasing in this way. Okay, so this is the problem size. Okay, what is the effect of how much time each algorithm will take on a computer with the 10 raised, this is times 1 billion steps per second computer is there. Okay, then the problem size is in this, and there are different algorithms. These are all different algorithms. This is one algorithm. It is the order of growth is n. This is another n log n. This is n square. This is n cube. This is n raised to 4. This is n raised to 10, and it is n raised to 2 raised to n. This is exponential time. So you can note this. Suppose n equal to 10, then suppose n is equal to 10. Suppose n equal to 10, you can note this. Okay, it's very interesting actually. Suppose n is equal to 10, then this is the linear time taking algorithm will take 0.01 microsecond. It is very low. N log base to an algorithm will take 0.03 microsecond. N squared take 0.1 microsecond. N cube will take 1 microsecond. N raised to 4 will take 10 microsecond. N raised to 10 will take 10 second. And 2 raised to n will take 1 microsecond. Okay. But then if n is equal to 20, similarly, we can calculate the time of each. And I'm interested in this here on. I'm interested here only. Okay. This case. Okay. So if n is equal to, suppose n equal to 100. You can consider this case, n equal to 100. Then how much time the algorithms will take? When n equal to 100, then you can note this. You can note this, how much time the 2 raised to n time taking, exponential time taking algorithm will take. It will take 4 into 10 raised to 13 years to solve it. It is year. Okay. So if n is equal to 100, then the exponential time taking algorithm will take 4 into 10 raised to 3 to solve that problem. Okay. It's a very big time. Okay. So that is okay. Similarly, if n raised to 10 complexity algorithm will take 3,000 years to solve the problem. But if n raised algorithm, n raised to 4 will take only how much time? 100 milliseconds. Okay. N cube will take 1 millisecond. N square will take 10 microseconds. N log n takes 0.66 and n will take 0.1 microsecond. Okay. Just so my question is, which will be the better algorithm? Which will be the better algorithm? Which will be the best algorithm? Dilna, which is the best? Dilna. Okay. Anyway, just try to understand. Depending on the input, different algorithm will take different time. Sometimes it will be days, years, or centuries to take a solve a problem. Okay. Just try to understand this concept. Anyway, today we discussed about the order of growth of the function. First, we discussed about the asymptotic notation. Second, we discussed about the order of growth. And then we discussed a problem and analyzed the time complexity, how the order of growth will vary depending on the inputs. Okay, 1 minute. Attendance left. Okay. Okay, in the late already attendance left. Already attendance left.